Today, I am presenting my project, Flow Heterogeneity Impact on Dissolution Behavior in Geologic Porous Media. First, I'd like to thank my advisor and collaborators for the immense help on this work, and I want to acknowledge the funding sources, the National Science Foundation and the Petroleum Research Fund. A useful tool in reaching net zero emissions is carbon sequestration, the process of capturing and storing atmospheric carbon dioxide. One method to do so is geologic carbon storage, where we inject supercritical CO2 into a confined brine formation in the subsurface. One concern of this method is that the sealing cap rocks, typically carbonates, may be dissolved by the CO2 acidified brine. Rock dissolution may create preferential or channelized flow paths where CO2 can escape and compromise carbon storage security. This motivates us to better understand and model the impact of fluid flow on solid dissolution in these brine rock systems. A classic view of dissolution behavior is shown in this phase diagram developed by Golfier and co-authors in 2002. Its axes are the dimensionless Peclet and Domkohler numbers, where the Peclet number compares the advective to diffusive transport rate, and the Domkohler number is the ratio of the reaction to mass transport rate. This diagram predicts that at low Domkohler numbers, we expect to see a uniform dissolution pattern, where the fresh reactant is carried away from the inlet and the reaction spreads throughout the sample. At higher Domkohler numbers, we expect to see one of two dissolution patterns: compact, if transport is slow and dominated by diffusion, where the porous medium is completely dissolved where the injection occurs, or wormhole, if transport is fast and dominated by advection, where highly conductive channels are etched through the rock where all the reaction occurs. This diagram and its supporting simulations were developed for the Darcy scale, assuming the underlying flow field is homogeneous and the velocities are Gaussian distributed. Real rock samples are rarely homogeneous. Let's plug some data of variably heterogeneous samples into Golfier's model. I use color to show the observed dissolution behavior from the post-dissolution flow fields and structures, and plot samples according to their known Peclet and Domkohler number. First, we plot the samples where we observe uniform dissolution. All of these samples correctly fall into the uniform regime defined by Golfier's diagram. Now, we plot the samples where we observe wormhole dissolution. We see that all of these samples were incorrectly classified by the classic model. A possible cause for this misclassification for wormhole dissolution patterns is the poor scale flow heterogeneity that this macroscopic model was not designed to capture. In this work, we are using these data to improve behavior classification and simultaneously predict reaction rates by considering the Peclet and Domkohler numbers and flow heterogeneity. In this project, our goal is to learn how initial flow conditions impact the reaction ratio and dissolution behavior. To do this, we performed a meta-analysis from the data shown on the previous slide because they report the Peclet and Domkohler numbers, reaction ratio, and the pore scale flow field. The objectives are to, first, identify the best way to describe flow heterogeneity in dissolution systems, and second, use the flow, transport, and reaction metrics to mathematically predict the reaction ratio and dissolution behavior. Our hypothesis of why flow heterogeneity is key to explain dissolution can best be explained with this pore scale schematic. Here, we have zoomed into the pore scale of a 2D velocity field. Once the flow field is determined, we can find the streamlines shown in white that show the direction a particle will travel. Flow heterogeneity can also be conceptualized as a division of the flow field into mobile and immobile flow regions, shown in white and blue respectively. When CO2 is injected into the rock, shown here as pink particles, the bulk of the injected fluid will travel through the mobile region. The CO2 particles are most likely to come in contact with the host rock at the interface between the mobile and immobile regions, shown in red. At this interface, the acidified brine locally mixes with the rock and reacts to dissolve it. Since the acidified brine is not equally distributed in the void space, mixing of reactants is incomplete. This is in stark contrast to batch dissolution, where the solution and rock are forcefully well mixed in a beaker by a stir bar. To gauge how incompletely mixed and underreacted a system is, it is typical to quantify a porous medium's reaction ratio, the ratio of the effective or measured reaction rate to the batch reaction rate. To convince you about the relationship between dissolution pattern and reaction ratio, I will illustrate the direct relationship between flow homogeneity, mixing, and reaction. The sample in red shows a structurally uniform bead pack that experiences highly homogeneous flow. The sample in blue shows a structurally complex carbonate that experiences heterogeneous flow. After the CO2 injection, some level of dissolution is experienced in each sample. We show the reacted rock surface in red and the unreacted rock surface in gray. In the uniform sample, the high flow homogeneity results in a higher mixing potential and increases reaction. For the complex sample, the low flow homogeneity locally restricts the mixing potential to the boundary of the mobile region and results in low reaction. The middle plot shows the temporal evolution of reaction ratio for both samples. Here, the uniform sample, shown in red, reaches a stable high reaction ratio, indicating the effective and batch reaction rates are relatively similar. Conversely, the complex sample, shown in blue, stabilizes at a lower reaction ratio, indicating that the effective and batch reaction rates are very different. The point is that more homogeneous flow fields lead to lower reaction rates. To quantify this effect, we first have to find a meaningful way to quantify flow heterogeneity. I will explain the 4 metrics we explored to measure flow heterogeneity. The first being the Earth mover's distance, or EMD, which is the minimum amount of work required to transform the observed velocity distribution into statistically equivalent Gaussian distributions, mathematically defined as the absolute difference between the 2 cumulative distribution functions. We measure the mean and variance of the observed initial velocity distribution and create a statistically equivalent Gaussian, the assumed distribution for a homogeneous flow field. This measure tells us how far away our observed velocity distribution is from a homogeneous one, and thus lower EMDs indicate a homogeneous flow field, and greater EMDs indicate a more heterogeneous flow field. The second metric is the percolation threshold, or PC, which divides the flow field into mobile and immobile regions, mathematically defined as the ratio between the minimum velocity in the mobile region relative to the average velocity of the entire sample. This threshold is set at the first established path of high velocity connecting the inlet to outlet. Velocities lower than this threshold are in the immobile region, and velocities greater than this threshold are in the mobile region. A small PC indicates that the velocities in the mobile region are close to the average of the entire sample, hence a homogeneous flow field. A large PC indicates that the velocities in the mobile region are much higher than the average for the entire sample, hence a heterogeneous flow field. The third metric is the dimensionless volume of the mobile region. In this metric, we estimate the fraction of the void space that carries the highly concentrated brine, as we've explained that this brine is restricted to the mobile region. Mathematically, this is the volume of the mobile region divided by the volume of the voids. If this volume ratio is small, then a small fraction of the void space participates in mass flux, acting as a smaller reservoir for reactive brine, capturing the effect of a heterogeneous flow field. Conversely, if the volume ratio approaches 1, then a larger fraction of the void space participates in mass flux, acting as a larger reservoir for the reactive brine, capturing the effect of a homogeneous flow field. The fourth heterogeneity metric is the interfacial surface of the mobile region. Similar to the volume metric, mathematically, this is the interface of the mobile regions divided by that of the grains. In this metric, we are capturing the interfacial surface where mixing is hypothesized to occur. When the dimensionless surface is closer to 0, the mobile region is spatially restricted, indicating a heterogeneous flow field. As the dimensionless surface approaches 1, the mobile region covers most of the void space, indicating a homogeneous flow field. Next, we assess the independence or correlation between the metrics of interest with this cross-correlation matrix. The data represented in this matrix came from the collection of variably heterogeneous data shown earlier. Each dataset contained information about the reaction ratio, Peclet and Domkohler numbers, and the initial flow field from which we calculated the 4 flow heterogeneity metrics. First, we observe that the heterogeneity metrics are well correlated and are consistent with their respective definitions. Next, we observe that the Peclet and Domkohler numbers are highly anti-correlated, indicating that both metrics are telling us the same information for this collection of samples. Finally, we observe the high correlation between the reaction ratio and EMD. Now we will use statistical methods to determine if this correlation is in fact causation. Recall that the Peclet and Domkohler numbers have been used to predict dissolution behavior at the macroscopic scale. Now we want to improve predictions of both dissolution behavior and reaction ratio by also considering a metric for flow heterogeneity from our potential candidates. To select the best combination of parameters that describe dissolution, we used a generalized linear model, or GLM, which produces a linear equation for the reaction ratio, shown as mu, as a function of some linear combination of Peclet, Domkohler, EMD, PC, V, and S as independent and or interactive terms. The various combinations are ranked by their AIC, an overparameterization penalty and goodness of fit measure, to identify the best statistical model. While not shown, please note that diagnostic checks were also implemented to verify common issues associated with GLM are not encountered in this model. The best model found so far is a linear combination of PC as an independent parameter and the interaction of Peclet and volume. PC independently captures the initial flow heterogeneity. The Peclet number captures the influence of the transport process, and the dimensionless volume captures the available supply of acidified brine for the dissolution reaction. Shown on the left is our observed data. On the x-axis is PC, and on the y is the Peclet volume interaction. The marker size is proportional to the reaction ratio, and the color indicates the observed dissolution behavior. Immediately, we can see the relationship between the reaction ratio and dissolution behavior, where larger reaction ratios are associated with uniform dissolution and smaller reaction ratios are associated with wormhole dissolution. On the right is the predicted reaction ratio of the solution space that our model was parametrized for. From this heat map, we see generally that as our PC increases, aka with higher flow heterogeneity, our predicted reaction ratio decreases. That same space is associated with wormhole dissolution behavior. At smaller PC, aka with lower flow heterogeneity, as the Peclet volume interaction increases, so does our predicted reaction ratio. We can interpret this from 2 viewpoints. One, at fixed Peclet, we expect that as the volume of the mobile region approaches the entire void volume, a higher reaction ratio and more uniform dissolution pattern should emerge. Similarly, at fixed volume of the mobile region, we expect that an increase in Peclet would more quickly supply reactants near the rock, thereby increasing the reaction ratio. Considering the inevitable uncertainty for models, we wanted to assess this for our parameter space. To quantify uncertainty, we performed a Monte Carlo simulation using the 95% confidence interval bounds of each fitted beta from our model. In the heat map on the left, we show the variance of a predicted value in our parameter space for 10,000 simulations of each XY space combination. From this, we observe that the prediction variance decreases with increasing PC or flow heterogeneity. Also, we see that our variance range is approximately 1 to 4 orders of magnitude smaller than that of our predicted value, indicating that our model performs substantially better than a random model. The key takeaways from this project are: 1, the reaction ratio and dissolution behavior are strongly related. 2, the flow heterogeneity plays a critical role in dissolution reactions. And 3, we can predict the reaction ratio and dissolution behavior using a sample's PC and Pecklet volume interaction value. The next steps for this work are to build up our data set to make the predictive model more robust. If you are interested and able to share your data set from a pore scale dissolution simulation or experiment, please email me and we can collaborate. Thank you.